Hello everyone and welcome back to another mini concept, this time about chemical kinetics. So chemical kinetics describes how fast any given reaction occurs, as seen on the screen. Now, when we think of a reaction, we normally describe it as, for example, A plus B turns into C. So when A reacts with B, it normally yields C. So this is a reaction. Now, how fast does this reaction occur? In other words, how fast does A turn into C or B turn into C? Because these two are constituents of what compose C. So, whenever we have chemical kinetics, we actually describe primarily how fast the reactants change. And when we describe that rate of reaction, we can use two different approaches. So, one is the rate expression, which is given to describe the rate of appearance and disappearance of both the products and the reactants. Now, what does that mean? Rate of disappearance and rate of appearance. Now, rate of disappearance is obviously going to describe what's used up in a reaction. Now, that's going to be A and B. So, this is for reactants. Now, when we write the rate of disappearance, it's typically written like this per reactant. It's going to be the change in concentration of, let's say, A over the change in time. And this is going to be multiplied to the reciprocal of its stoichiometric coefficient. Or in this case, there's none, so it would be just 1. Now let's say that if there were a coefficient here in this reaction, let's say that if there were 2 moles of A reacting with B, it would be the reciprocal of 2, which is 1 over 2. So the rate of disappearance for A would thus be the delta of the concentration of A over delta T, and then it would be, rather delta of the concentration of A over 2 times the change in time. Or it can also be separate, 1/2 times delta A over delta T. So that would be for reactant A. Again, reactant A. However, one more key thing to take note of for the rate of disappearance is that we're describing a loss. So that means that we must always have it in negative. So for the rate of disappearance or the rate expression for reactants, we always have it in a negative sign. Now how about with B? So let's just give that a try. So for reactant B, we'll start again from drawing our base rate expression without the coefficients. So that's going to be the change in the concentration of B over the change in time. Now its stoichiometric coefficient is just 1, so 1 over 1, that's basically it. And this is going to be our rate of disappearance. However, we always have to add the sign. So there it is. And that's our rate of disappearance for our sample reaction here. Now, how about for the rate of appearance? Well, rate of appearance is for what is being produced. And the rate of appearance describes thus the products. Okay, so now what's so different? Well, really, there is no difference. It's just going to be the same thing. And what changes? If here, the negative sign is put in there so that we can signify that there's going to be a decrease of that certain substance, or rather we're using up that substance. Here we're just going to keep everything in positive. So let's actually put another coefficient here. Let's say that 2 moles of A react with 1 mole of B to produce 3 moles of C. So let's try doing that for our rate of appearance of C. So the rate of appearance of C would thus be the change in the concentration of C over the change in time times the reciprocal of 3. So that's 1/3. And this is thus the rate of appearance. Now, if you want to add the plus sign, you can also do that. Now, how would one solve for the rates of appearance and disappearance of certain substances based on the rate expressions? Well, that's quite simple. It's going to be, let's get rid of this. So, all of these are actually equal to one another. Because obviously, the rate of disappearance or basically the rate of one side must match the rate of the other. In other words, the reaction is happening simultaneously, right? And if it's happening simultaneously, then one substance can be finished first. No, one substance can be finishing faster than the other. However, they would finish at the same time. And factors that make one substance finish faster than the other could be, for example, its molecular weight or the other circumstances of the reaction, right? The states of the substance and whatever. So these are all actually equal because their rate needs to be not constant. Their rate needs to be equal between the three because it means that the reaction will happen and finish at the same time. So let's say that the rate of disappearance of reactant A is equal to 3 molars per second. So let's say that the change in A time is equal to 3 molar per second. And we want to find the rate of B, the rate of disappearance of B. So we want to find delta B. What would we do to solve for this? Well, seeing that they're all equal, we can actually disregard the right side with C and just focus here on these two. So allow me to nudge this a bit up. Oops. Okay, let's just move this up a bit. There. This up as well. Okay, so going from here, we can substitute this. We'll put in our negative 3m per second times 1/2. This would give us a final answer of 3/2 molar per second is equal to negative change in B over change in T. And this is actually our answer. So this is going to be the rate of disappearance for reactant B. Now, can we solve for reactant C? Well, we actually can. So now we know that the rate of A is going to be 3 molar per second, and we know that B is going to be 3/2 molar per second. So C can be derived using either one of these values. So let's try getting C using our value of B. So C is given by 1/3 change in C over change in time. We want to get this, so we're going to isolate the right side. And we do that by multiplying 3 to both sides, because 3, the coefficient of the rate of disappearance of rate of appearance of C is a fraction. So 1/3, to remove the fraction, we multiply 3 to both sides, cancel. Here, multiply 3. So Our answer for the rate of appearance of C would thus be 9/2 molar per second. And this is our answer there. So now we can remove all of this, and we can show that our final rates for the overall all these substances here are the following. So for reactant A, the rate of disappearance of A would be 3 molar per second. The rate of disappearance for B would be 3/2 molar per second. And the rate of appearance of C would be 9/2 molar per second. Now, as I mentioned earlier, this is just one of the two ways that we can describe a rate of reaction. Well, one of the two ways that we're going to be talking about in this video. So the next one is actually the rate law. So let's take this reaction and I'll copy it over here. Okay. And let's bring this all the way here. Okay, so a rate law is more of a mathematical approach to getting the rate of a reaction. However, this is just a general term. The term rate law is actually a general term because there are differential rate laws and there's also integrated rate laws, which we will talk about in another video. So for this one, we'll just go over the base definition of a rate law. We're not going to go into how to solve it because that's quite lengthy, and we'll have that in the next video. So the rate law is given by the following equation. So the rate of a reaction is equal to the rate constant times the concentration of reactant 1, which is A, raised to the power of m, and this is multiplied to reactant B raised to the power of n, where m and n are equal to the order of the reactants. Now, when we talk about the order of a reactant, I want you guys to think about the relation of the concentration of one substance to how fast it's going to be consumed. And well, we easily simply put, the rate of a substance is going to be changed based on the concentration of a reactant. Well, the larger the concentration, the faster the rate. And of course, different substances also have different relationships with its own rate. Some substances are completely separate from their some substances concentration are completely separate from how fast it gets consumed. While on the other hand, other substances react faster or are consumed faster the larger that they get, the larger the concentration, and some are just standard. So it's all dependent on the order, which we will talk about more in the next video. So let's take this moment to stop from the math first and just describe what does it mean for a substance to react. So right now we're talking about how fast it reacts, but what are the factors that actually change the rate of a given reaction? Well, one is the fact that based on collision theory, oops, particles or atoms have to collide. Obviously, well, the name of the theory is collision theory, so they have to hit each other. So atoms need to hit each other, and when they hit each other, they need to align. Think of the water molecule. So we have H2O. Now, H2O tends to bond through hydrogen bonding by having the atoms of the molecules of H2O align like this. So the O would attach to the H, and then that continues on. So each would have there. And these hydrogen bonds are continuous. So they run through the liquid and solid water, and in solid water they actually form a crystalline structure. But that's beyond the point. Basically, they need to align. They need to make sure that they're oriented in a way where it can actually form a certain substance. For bonding can't happen if you don't have the right substances beside one another. If we had in water, if we had H bond to H again, well, that kind of doesn't make any sense, right? Chemically speaking. Now, what else? What's the last requirement? It needs to have enough energy. As we discussed in thermochem, every reaction has an activation energy. And in order to have a reaction occur, you need to overcome this activation energy. You need to activate the reaction. Now, what helps here? What factors change these circumstances? Well, the factors that can change these circumstances are one. Hold on. Let's have this in yellow. So factors are one, the concentration. Again, the more of a substance we have, the faster the reaction. Now, the more substance that we have means the more that has to react. Now, if you try to cook a blob of food, cooking that blob of food will take quite a while. Sure, there's a lot of food. However, cooking the entire thing all at once is quite a challenge. So what would we do in order to make sure that our food cooks evenly, our food cooks fast? Well, we increase the surface area. When we increase the surface area, such as by cutting it up or by cutting it up, we increase the amount of substance that's actually reacting at a time. So the concentration would still be the same. We would still have the same mole over volume, mole per liter. However, this time we're just lowering the amount that's reacting all at once. And lastly, the presence of a catalyst or an enzyme. In biochem, catalysts are present as enzymes, and enzymes are proteins. So whenever you see a reaction that looks like this, let's say that it's 2A plus B, in the presence of an enzyme as a catalyst, yields 3 moles of C. So this is completely read as 2 moles of A react with 1 mole of B in the presence of an enzyme to create 3 moles of C. The catalyst here would be the enzyme. Now, obviously, this would speed up. This would speed up a reaction. So if you want to slow it down, you would want to do the opposite. So hold up. If you want to speed it up, you do this. You increase the concentration, the surface area, and add a catalyst. However, you want to slow it down, you just decrease the concentration, you decrease the surface area, and to increase the activation energy rather. So again, sorry, that's something I haven't mentioned. A catalyst decreases the activation energy. If you want to slow down a reaction, you add an inhibitor. So these two are opposites. So inhibitors increase activation energy. This decreases it. Okay, there. Essentially, catalysts are a different way for the reaction to process. It's a different pathway. It's a different area or manner that the reaction could actually begin. While an inhibitor does the opposite of that. It blocks it, or it essentially kind of locks it in a certain manner of reacting. That's why it's called an inhibitor. And that actually is where we will end this video. So I hope that you all learned something. This last part was a bit of a discussion. However, it's quite critical so that you can understand how the rest of the topic on chemical kinetics would work. So again, thank you everyone for watching, and I hope you guys learned something. I'll see you guys in the next video on how to solve for the rate of reaction using the rate law. So thank you everyone, and goodbye.